Okay, recording is on. March 8th, Math8680. And we reached kind of a somewhat satisfying point after we had proven that the boundary complexes of simplicial polytopes, those are nice simplicial spheres, simplicial complexes, triangulating spheres. And we proved a bunch of their properties using shellability. So we deduced Dane-Somerville equations, symmetry of the H vector that is, and we finished off the proof of the upper bound conjecture, and we proved that there's this degree map when you take the Stanley-Riester ring mod a certain linear system of parameters. And we even deduced something stronger than Dane-Somerville, is that quotient ring has Poincare duality, and then that degree map or evaluation map is very important in stating that. So now we're going to come back and do some things that I owe you. There are certain words that keep coming up over and over again. There are certain secrets that I've been keeping from you, and maybe it's now time for me to reveal some of my cards here. So I'm going to come back and talk a little more about fans, in particular, where do my mysterious linear systems of parameters that I keep writing down come from? I'll reveal that secret. More about systems of parameters, not just linear system of parameters, but we should talk about homogeneous systems of parameters and graded commutative rings. And this relates to this notion of Cohen-Macauliness. When is it that when you mod out by them, the Hilbert series behaves the way you wanted it to for the original ring and the quotient? Or when is the original ring a free module over this subalgebra generated by the parameters? And then Poincare duality is going to have to do with Gorensteinness. So we should talk more generally about both Cohen-Macauliness and Gorensteinness are really important. So let's get to it. Any questions about anything before we start dealing with some of these loose ends? Okay, I'm happy if there are no questions right now because I don't have anything to flip back to. We started a new set of notes. This is batch 6. Good. So fans, let's get back to fans. And where have our secret choices come from? Our secret linear system parameters. Well, I am going to tell you, when I have a simplicial fan, when all of the cones in my fan are simplicial, meaning their rays can be spanned by linearly independent sets of vectors, then there's actually a simplicial complex running around that maybe you've already realized that this was already true, but we want to give a name to this construction. So if I'm given a simplicial fan, and I'm going to call that sigma and RD, and I'm going to name all of its rays for all of the cones, rays row 1, row 2, up through row n. One can associate a simplicial complex, delta of sigma. That's going to be on the vertex set 1 through n. So basically on the set of rays, but I'll just use their subscript. Let me call it over here, delta sigma on vertex set 1 through n. And it's going to have a face. I have to tell you which subsets of the vertices 1 through n form a face. It's the ones such that their corresponding rays form a cone. Whenever span a cone sigma, in other words, remember these cones were always supposed to be non-negative integer combinations. Oh gosh. Yeah, let me okay. Sorry, I'm getting into this usual trap of multiple subscripting. So Okay, we should just immediately go to an example before we worry too much about the words that I've written here. Example. Well, suppose I take this complete fan in R2 that I think I've drawn for you before. I think it's the face fan of some simplicial polytope. Maybe here's my axes. Origin is a cone. Positive y-axis, positive x-axis are cones. Maybe we're going to call them row 1 and row 2. They're rays in the fan. Row 3 is negative x-axis. Row 5 is negative y-axis. Row 4 is pointing in the negative 45-degree direction. And in between, I've got some cones. Sigma 1, sigma 2, sigma 3, sigma 4, and sigma 5 are these two-dimensional cones that look like infinite pieces of pizza. Okay. And so this thing is going to give rise to a delta sigma, which has the subscripts on the rays that show up, 1, 2, 3, 4, 5, as vertices. They correspond to vertices. So I'm going to draw you a geometric realization. Vertex 1, vertex 2, vertex 3, vertex 4, and vertex 5. And whenever I have a cone, sigma 1, for example, and it's the non-negative span of row 1 and row 2, then I put in the face F1. This facet is 1, 2. And because I got the cone sigma 2 that's on row 2 and row 3 is what non-negatively span it, I get the associated edge 2, 3 corresponding to cone 2, sigma 2, F3, F4, F5. Seem okay? And, you know, let me just emphasize, we're also going to be dealing with some things that are not complete. So let me take this sigma prime, that's a subfan of this. And I don't know, let me just take row 3, the origin, row 4, row 5, row 1, cone sigma 5, cone sigma 4, and no other cones. So just being a subfan means, right, whenever I've got a cone like sigma 5, I have to have the rays that are contained in it as faces, and the origin there is also there as a face. And this thing, of course, gives me a subcomplex for its delta sigma prime. Right, it's just going to be the 3, not the edge 3, 4, but the vertex 4, the edge 4 to 5, the edge 5 to 1, the vertex 1. And notice, even though I said that it's on vertex set 1, 2, 3, 4, 5, we're allowed to omit vertices. That's okay. Even though in principle they could be there, there's like a ghostly 2 that's missing, vertex 2. And of course, this is a subcomplex as a simplicial complex of delta sigma when we had a subfan. And even though this two-dimensional example doesn't make it clear, why was I assuming that I had a simplicial fan sigma? It's because in the higher dimensional case, if I had had one of these things that has like a square cross section, then when I draw these pictures, I would have needed square faces, and that's not in a simplicial complex. You don't have faces that are squares. That would be a polyhedral complex. We're not talking about those, even though one could. And that's what corresponds more generally when you have fans that are not simplicial, where they have polyhedral cones. You can still build something that's called a polyhedral complex associated with it, but we won't need those in this class. Is everybody okay with this construction of sigma to delta sigma? Questions? One thing that you might notice immediately is like, what is the, you can say something about the homeomorphism type of delta sigma having to do with the way this fan sigma sits inside of space in R2. And so note, or this is really maybe a note, an exercise. Actually, let me do this. I'm gonna say it and then draw it in this picture and then write it. My claim is that when you look at what the geometric realization is of delta sigma, notice here it's a circle. I claim it makes sense to think about that as being this circle, the unit circle inside of R2, intersected with our fan, decomposed by the fan into these, oh, let me try that again. These segments that look like edges, but they're curvy. And similarly, this one here, if I took the unit circle inside of R2 and intersect it with my fan, well, I'm going to get this vertex, this edge, this vertex, this edge, this vertex, and then this lone vertex over here. And sure enough, that pink stuff, the unit circle intersected with the fan up here, looks like it's homeomorphic to the delta sigma prime there. And that's true, and it's not hard to show. So let's just notice that remark. It's not hard to show that the geometric realization, right? So we have delta sigma, that was an abstract simplicial complex, the way I define it, but I draw these pictures that look like it's geometric realization. And that's something I told you how to define it carefully way back at the beginning, right after the overview, when we started talking about simplicial complexes. Abstractly, we said, oh, there's a way to always build them in a high dimensional space as an actual topological space. It's always homeomorphic to, if it came from this fan, the union of all the cones in the fan. So this just means union of all those cones in sigma inside of RD. That's a topological space. It's got the subspace topology. And then just intersect it with the unit sphere. Let me call it SD minus 1. So, and I mean unit sphere about the origin. It's not so important that it's the radius of the sphere is unit. What's important is that it's centered at the origin. Okay, so let me, nobody get it? Let me emphasize that unit sphere is the thing that I was making pink in the previous picture. Questions about this? In particular, in the complete fan case, right? When the fan is complete, you're going to get the whole unit sphere. And so that's the situation where this delta sigma is going to end up being a sphere up to homeomorphism. So in particular, just that is an important special case. Whoops. And it's an if and only if. Ah, missed. Why am I writing so small? I don't know. Remember, complete fan just meant that its union was all of RD. Okay, covered the whole space. Any questions about this? All right, so this is supposed to be me eventually revealing some secrets about the systems of parameters. So let me get to that now. So suppose the rays
Vic, can I ask a quick question?
Yeah, absolutely.
When you say unions of cones at sigma, little sigma and big sigma, cones don't have to be maximal dimensional, right?
Oh, absolutely not.
Okay, great.
But on the other hand, right, I mean, so a good example there, Zach, would be, I do need to take row 3, right, as part of that when I'm talking about the union of sigma. But, you know, when you were saying that, like row 5, of course, is already contained in sigma 5. So when I'm worried about what's the union, well, then you only need to take like the facet cones, the cones that are maximal under inclusion, because I was thinking of them as closed cones when you're worried about the union. And Sam's comment is, not all triangulations of spheres are of this form, right? These are exactly the PL spheres. Yes, this is, so there's this interesting part of topology called piecewise linear topology that worries about piecewise linear homeomorphisms between spaces. And that's right, one way of saying the spheres that arise in this way from complete fans are what are called the PL spheres, the piecewise linear spheres. Not all spheres are PL. An example that we kind of talked about a while ago that wasn't PL, the first famous example is you take this Poincare homology 3-sphere and you suspend it twice and you get a 5-dimensional sphere, which is definitely not achievable in this way. It is not PL. Yeah, thank you, Sam. Good. Okay, so where am I going to get some systems of parameters from fans? Suppose the rays in my fan, you know, R1 through Rn, sigma, have natural choices for the vectors that span them. This is true when we take face fans of polytopes, for example. So I'm saying rho I is just the non-negative span of vector vi. And, you know, let me just, for example, if sigma is face fan, how do I do face fan? Calligraphic F, P for P, a simplicial polytope. And we'll be doing an example like this in a moment with vertices where the VIs are the vertex vectors. And I'm assuming my simplicial polytope is d-dimensional and it's got the origin in the interior when I say all this stuff. Then I'm going to tell you how to get from a linear functional, something in RD star, I'm going to tell you how to get a theta, a linear parameter, somebody who lives in the Stanley-Riesner ring and is of degree 1. And for any functional, linear functional, F in RD star, get an element theta sub F that's going to live in, okay, here is the Stanley-Riesner ring for the simplicial complex, delta sigma, in degree 1. So it's a linear, you should think of it as part of a linear system of parameters, maybe. Defined like this, all you do is you say theta F is equal to, you sum j goes from 1 to n. There are, for each vertex, sorry, for each ray, there's a vertex variable in here, right? Oh yes, let me emphasize again. Where is this going to live? It's going to live in this Stanley-Riesner ring. Remember who that is. It's got variables, and then it's got some relations that you mod out by. And I'm going to tell you what coefficient to put on the variable xj in the list of variables. So this thing lives in degree 1, and you take that linear functional and you evaluate it on the vector vj. Okay, so this thing is a real number. That's a coefficient in front of a vertex variable. I'm going to do some examples. I know it's a lot of notation, but here's the point. Where is this? Yes, proposition definition. Prop def. in the above setting, so I mean any fan in RD, and you've got some choices of vectors that span its rays. What am I going to say? We can find. I'm going to call this theta underbar sigma is this theta 1 up through theta d. And really what they are is theta f1 up through theta fd, but I'm trying to avoid the double subscripting. They're going to live in the Stanley-Reisner ring. They're all going to be degree 1 elements. They're going to be a linear system of parameters in the sense that I've already defined LSOP by just taking a basis for the functionals for the dual space and just calling them F1 through FD and making these elements by picking any basis. Any R basis. Of functionals. And these thetas are going to form an LSOP, linear system of parameters. So I'm going to remind you what that means. Just means that if we quotient the Stanley-Reisner ring by the ideal that they generate, if we set them to 0, we're going to get something that's finite dimensional over the field. No longer has infinitely many graded pieces. No, it stops after finitely many. Or another way of saying it is, these elements, they will generate a subalgebra. It's actually going to be a polynomial subalgebra, and the whole Stanley-Reisner ring is a finitely generated module over it. I.e., this is true. Is finite dimensional over K. And we saw early on when we're in this graded ring situation, another way of saying that is the whole Stanley-Reisner ring is a finitely generated module over the subalgebra that they generate. And these are the things that I keep pulling out of my pocket, is these theta sigmas in the various examples that we've been doing that I knew ahead of time would definitely be linear systems of parameters. I'm about to do an example before I prove this. It's going to be easy to prove. What we really want to do is understand why is it that these are the ones that have been showing up in our examples. Questions before I do an example or two?
Wait, sorry, I'm confused, Vic. Is being a regular sequence part of the definition of linear system of parameters or no?
Absolutely not. These will not always be regular sequences.
Okay, I was very, very confused about that, but now I see what you're saying. So they don't have to generate a polynomial algebra, or they will?
I should be careful. Yeah, hold on. Actually, you're correct there, Sam. I've stated this incorrectly. If my complex is not d-dimensional, they are not going to be a system of parameters even. It's not just that they won't be a regular sequence, but they won't even be algebraically independent. So I'm going to take out that part, which is wrong.
Basically, we're just saying, oh, wait, now that it kills enough things is what you wanted to say.
That's what I want to say. But thanks, Sam, you just stopped me from saying something wrong. To make what I said correct, Sam, I would have had to assume that there's at least one d-1 dimensional face. In other words, that the dimension of delta matches the dimension of the ambient space.
Yeah, I don't think that was my main source of confusion, though, was about the regular sequence business, which I bet you're going to mention in a second. Sorry.
You accidentally corrected me, but that's good. Thank you. Okay. Yeah, I'm mostly going to be caring about situations that look a lot like this, where even when it was a subfan, there's at least one top dimensional cone. But even that, what I just said, now is a little bit of a lie. When we talk about Bergman fans of matroids, the subfan we're going to be talking about, and we are going to apply that proposition that I just proved for Bergman fans. It has dimension r-1, where r is the rank of the matroid, whereas it's living in a space whose dimension is n-1, the number of elements, where n is the number of ground set elements in the matroid. So there will be a mismatch in some of the situations where we're applying this lemma, where all I want to know is that it's finite dimensional or a finitely generated module over the subalgebra. I won't care so much about whether that's a polynomial ring, and I will not care about whether it's a system of parameters. Technically, it won't be a system of parameters. You're modding out by even more than a system of parameters. Sorry, I shouldn't have said any of that. Too much information. Can I do an example? Okay, most important example that's coming up for us are when I take P, a simplicial polytope, I take the VIs to be its vertices, and I take sigma to be the face fan. Let's just do one yeah, here's some coordinates in R2, and maybe I'm going to make 1, 0 and 0, 1, and stop me when I make the wrong coordinates. You've seen me do it before. Okay. So that's V1, V2, V3, V4, and V5. And here's my simplicial polytope. All polytopes in 2 dimensions are simplicial, but that's okay. And there's the origin in the interior, and maybe we should, what the heck, color it, why not? That's P. And so when I make the sigma, it looks like that thing that I had before. In fact, why not? Let's just steal it. Oh, actually, we got both of them there. Let's steal them both. Oh, didn't mean to do that. Okay, try again. All right. And so just to introduce some separation here. That's not straightening out. Try it again. That's straightening out. So this is the that's the face fan. And that's the delta sigma there. And now who are the thetas? There's going to be 2 of them. Let me just pick as my basis for the linear functionals on here the usual thing, the thing that you label the axes with, x1 and x2. In other words, x1 is the coordinate function that reads off your x coordinate. x2 is the coordinate function that reads off your y coordinate. Okay, so if I'm taking f1 is x1, f2 is x2, then the theta 1 and theta 2, well, it's very simple. If I try to read them off in terms of what they do on the various vertex variables, or on the x1, I don't know whether to label these. Let me call these x1, x2, x3, x4, and x5 to give you the coefficients. You just write down the coordinates of the vertices. Oh, this is terrible because I used the functionals. I called them x1 and x2. Ah, horrible. I'm going to take that away so as not to confuse you. I'm using the standard linear functionals, the coordinate functionals on R2. I'm not going to name them. But the point is, you look at vertex V1 and you write down its first coordinate and its second coordinate. 1, 0. You look at the vertex V2, you write down its coordinates. I see a 0 and a 1. And then x3 is -1, 0, x4 is -1, -1, x5 is 0, -1. And And that tells you those coefficients, how to write down the thetas in terms of the vertex variables. Theta 1 is x1 times 1, x3 times -1, x4 times -1. It's x1 minus x3 minus x4. Theta 2, I read off these coordinates and I put them in front of the x2, the x4, and the x5, and I keep it x2 minus x4 minus x5. And so the claim is that when I take this thing, this is going to be finite dimensional over the field. Or if you like, this Stanley-Reisner ring, which would have had 5 variables, I mod out by some non-faces. There's actually going to be 5 minimal non-faces that I would have to mod out by, it turns out. Whatever it looks like, this Stanley-Reisner ring, whatever it looks like, is finitely generated as a module over the subalgebra generated by theta 1 and theta 2. I know that will be true once we prove this proposition. Okay? Let me do another example. That was really example 1.
Can I pause there? You said we will know this will be true.
Because I haven't proven this yet, Zach.
Yes, we have theorems for this specific example that would prove this is true directly, and this is sort of a general theory. Is
right. So I will, in the proof, I will show you why each of these minors that corresponds to a face here, I have to convince you why that thing had maximal rank, that submatrix. But in my proof of the proposition, I have to use something about functional, simplicial, blah, blah, blah. Sound okay? Good. Yeah, so what about an example that we did more recently? Let me try and draw it more carefully, this bipyramid where I wrote down some theta 1, theta 2, and theta 3 that looked pretty good, but here's where they came from. My bipyramid had a vertex up here, a vertex down here. I'm going to try to make that vertex be E3 and this one negative E3 in a 3-dimensional space. But in the XY plane, let me carefully coordinatize it. There's the origin. That thing's on the z-axis. That's also on the z-axis, negative z-axis. Yeah, let me put a vertex here. What am I naming these vertices? Oh, I named them A, B. Okay, this is going to be vertex B is going to be E2, standard basis vector E2. Vertex A is going to be its standard basis vector E1. This is vertex D. This is vertex E. And I am going to put at -1, -1, 0. So this is the last vertex is C is at minus E1 plus E2. Let me see if I can draw this. This is supposed to be a bipyramid, and so it is. All right, let me do a little coordinatization. Those are supposed to be tick marks. And here is the bipyramid. Okay, so it's some version of this bipyramid that I would just slap down on the page less carefully before because I didn't need its coordinates. But, if we look at if we let sigma be the face fan, we look at the delta sigma as this bipyramid that we've talked about before. Oops. Slapping it down a little faster there, okay. And we looked at the Stanley-Reisner ring before and said, oh yeah, it's got vertices A, B, C, D, E. The minimal non-faces were particularly easy, like vertex D and vertex E are not forming a face, and that's one of the minimal non-faces. Another one is ABC is a triangle that cuts through the middle. That's not a boundary face. And so it's DE ABC. That's a presentation for the Stanley-Reisner ring. And so the claim is that I can get some theta 1, theta 2, and theta 3 if I take the standard functionals and use them as to get the coordinates on the vertex variables A, B, C, D, E by saying like, oh yeah, A, let me write down its coordinates with respect to the standard linear functionals. First functional 1, functional 2, functional 3, namely its three coordinates. So it is 1, 0, 0, B is 0, 1, 0, C is -1, -1, 0, D is 0, 0, +1, and E is 0, 0, -1, if I didn't make a mistake. And then that lets me write down the thetas as what's going to be theta 1 is going to be A minus C, theta 2 is going to be B minus C, and theta 3 is going to be D minus E. And you saw me work with, modding out this ring, mod the ideal generated by these thetas. This is where we were illustrating Poincare duality, was exactly in that ring. Right, so for example, we showed that in this case, this turned out to be, okay, so it's A, B, C, D, E, blah, 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 D, E, A, B, C, A minus C, B minus C, D minus E. But I also showed you it was isomorphic to like K adjoin A and C, and I think we modded out by what, C cubed and A squared or something? No, E squared. Remember that was the one that we worked with? Definitely finite dimensional over the field.
I think you want to say K adjoin E. And
Yeah, I definitely do. Thank you, Colin. Let me make that bigger to fix it. Yep. We left ourselves, we got rid of we said A is equal to C, B is equal to C, and D was equal to E. So we got rid of the A, B, and the D. Yep, good. Okay, does everybody see where I've been pulling the mysterious thetas from? All right. So let's check why these mysterious thetas always work. Any questions before we do that? Yeah, it's practically by definition. Let's see, proof of proposition definition. Yeah, so we have this criterion that we've been referring to. Recall that theta 1 through theta D, when you're in a Stanley-Reisner ring and you take a bunch of linear elements, right? The linear case is the easiest one to check when you've modded out by enough stuff to make it finite dimensional. Have finite dimensional over K, which is the same as, what we're talking about, or the whole ring finally generated over their subalgebra. If and only if you check for every face F of delta, these restricted things. So you take those thetas, you just set to 0 all the variables that aren't on that face. Or if you like, in the matrix that defines the thetas, you only look at the columns that are indexed by the vertices in F, the face F. And you just focus on that set of coefficients or that set of columns. And for every face F, those things have K span of rank F. Excuse me, the cardinality of F. They span a space whose dimension is the cardinality of F, which is as big as it could be because you've restricted them to the variables that are just in the face F. Okay, everybody remember this? We proved this quite a long time ago. although this took a little bit of work. This is one of those things where the interesting direction, the backward direction, was the one that used these like induction on the number of faces and some tiny little short exact sequences that were really not terribly complicated. All right, and this is the same, checking it for every facet, but let's think about this. Now that we're in this situation, right, delta came from this delta of sigma. It came from one of these simplicial fans. And we had, the way we got these coefficients on the thetas, we said, oh, the rays in the fan, they gave us the theta coefficients. We evaluate them on those vectors, the VIs that spanned the rays. So another way of saying this is, for every cone, sigma of the fan, our simplicial fan sigma, what are we saying? Let's say sigma is, I don't know, r greater or equal to V1 plus, do I have to do VI1? No, I'm going to do just V1, Vs. Forget the double subscripting. So if it's a cone that's spanned by these vectors V1 up to Vs, that simplicial cone, we have oh yeah, sorry. I skipped a line and I was looking at my proof and saying, wait, that seemed too early to conclude that. We have that these functionals, when we take the I functional, we evaluate it on the jth vector. We form that matrix, which is going to be the coefficient matrix for the thetas restricted to that face. This matrix, I going from 1 to D, because our FIs were a basis for the dual space, J going from 1 to S. So J is the columns indexed by F, is a matrix of full rank. In other words, of cardinality S, of rank, excuse me, of rank S, which is the number of vertices in our face, i.e. maximal rank. Number of columns. In other words, its columns are linearly independent. Everybody agree that was our criteria, you know, where you check the matrices and you checked the coefficients, but now in this particular case. Okay, but those V's, remember, this is, you know, we got this cone sigma. It's got these, here's the origin, here's the V's, V1, V2 up through Vs. We're spanning this cone sigma, right? This cone sigma is supposed to look like, I don't know, you know, this thing. You take a basis of functionals, you evaluate it on a bunch of linearly independent vectors, right? It doesn't really matter what basis of functionals you pick. You pick a different basis of functionals, you're just going to be changing the, what is it going to be? The up to row span, what this matrix look like. We're saying that the coordinates of V1 through Vs actually have maximal rank. They have rank S because they're linearly independent vectors. I don't know. I'm just going to write this. This is if and only if V1, V2 up through Vs are linearly independent. Because it's a basis of functionals you've taken. Right? What you're doing here is you're just saying, let me write down using F1 through Fd as my functionals, as my coordinates on RD. Let me write down the coordinates of these VIs. Yep, it's going to span a matrix whose rank is S, the number of VIs or VJs, because they're linearly independent, right? We assumed it was a simplicial fan. Let's pause there for a second and see whether we believe that. Questions? Okay. Now, what may seem a little weird here is I had to pick some VIs, I had to pick some functionals. Oh, Trevor asked a question, sorry. Why does the matrix of the bipyramid example have linearly independent columns? But they can't be, right? Sorry, the matrix of the bipyramid? I didn't understand your question, Trevor. This matrix, this matrix certainly doesn't, because they're like in R3 and there's 5 of them. But
right. And I guess I meant to ask why are those linearly dependent, and that you said they had to be linearly independent in the claim below?
No, so what has to be true, right, is take, for example, that's a face, and that's ABD. So the ABD submatrix, that has to be linearly independent.
Oh, I see. Thank you.
And same for any other face. All these 3x3 minors, they better be linearly independent, and that's checking this condition. Everybody good? Okay. So I'm actually going to get rid of 2 things that might have. Oh, and Zach said something. The linear dependencies are all the non-faces. Yeah, but Zach, actually, I don't even care whether on the non-faces they're dependent. That doesn't matter. If I picked like the entire matrix of theta coefficients, totally generic, like if I had transcendentals around, every single column is going to be independent. But all I care about is that on the faces, it's, I don't have any dependencies. Yeah, good. Okay, there's 2 ways in which this might seem unnatural. Me choosing those vectors VI that span the rays, I'll get rid of that later when we start talking about piecewise polynomials. That unnaturalness completely goes away. Trust me on that. That's the more magical thing. But the choice of the FIs, you shouldn't care about. So let me remark here. Choosing the basis the choice of F1 through FD as a basis for the functionals, a basis of RD star, that clearly makes no difference in what counts about the theta 1 through theta D. Yes, to write down a theta 1, theta 2 up to theta D, I needed the functionals. But all I care about is the subalgebras that the thetas span, or the linear span of the thetas. Those are all the same if I change the basis F1 through Fn. So I'm going to say in the K span of theta 1 through theta D within the Stanley-Reisner ring, or the ideal that they generate, or the subalgebra. Right, because if you pick a different set of coordinates on your space, right? Yes, I will be writing down some different linear combinations of vertex variables in each row, but I will be able to write your choice and my choice can be expressed in terms of each other. In other words, you will affect the individual thetas. You will not be affecting the K span. I shouldn't be saying K span. This is R span. Sorry about this. Suddenly my field K is R. I should have said that at the very beginning. I will not be affecting the R span. Let me actually think about this. Right. If I'm going to take my my coordinates in R, I better be using K equals R. Okay, let me not worry about this. But the point is, it doesn't matter which basis for the space of functionals that you pick in order to write down those thetas. Okay, this is probably a good point to stop. So what are the other loose ends we have to tie up? They're significant. I keep talking about linear system of parameters. I want to talk about homogeneous system of parameters. I want to relate it to regular sequences and Cohen-Macaulay rings and Gorenstein rings and our Poincare duality, and just like a whole bunch of things that if somebody said, ooh, you learned about Stanley-Riesen rings and commutative algebra, we'd be embarrassed if I hadn't told you these other things about them, even though strictly speaking I don't need them for the Kähler package, but I just feel like we gotta talk about them. So that's where we're heading next. Questions before we turn off the recording?